Today's topic of discussion is electric field. So we already discussed about Coulomb's law, and Coulomb's law is all about how two stationary charges interact, how they apply force on each other. And we got that two charges apply equal forces on each other, and these are actually action-reaction forces. So magnitude of the forces are same, but directions are opposite. Now today, we want to discuss a very significant concept, a very important concept, which is called electric field. You see, this is a positive charge, positive or it may be negative. It may be positive or it may be negative. Let us consider it to be positive. Suppose that it is a positive charge and it is another positive charge. Okay. Now you see this charge at the center. This charge at the center, actually it is creating a region around this. This charge at the center is creating a region. It is creating a region around it. So what will happen in this region? If another charge enters into this region, it will feel the force due to this charge. Now, this is a charge, suppose it is a capital Q. This charge is capital Q. So this capital Q charge is forming this region around it, and within this region, another charge, another positive charge, small q, is entering. So now this small q charge will feel the repulsion due to the capital Q charge. But outside the region, this small q charge will experience no force due to this capital Q charge. Only inside this region, this charge will feel the force. So every charge, when placed, it creates some region of its influence around it, and this region is called the electric field. Any other charge, when enters the electric field, will experience electrostatic force due to the charge which is creating the field. So this big circle is representing the okay, so it is representing the electric field. It is representing the electric field of what? It is the electric field due to the charge capital Q. Okay. Now this small charge, charge small q, if it is within this electric field, it will experience force. Since both charges are positive, so if this charge, small q, enters into this region, enters into this field, then it will experience repulsion. But if this charge is outside, then it will experience no force. So we can show it like this here. Suppose the position of the charge is this one. It is small q charge. Now here here it is experiencing force, but it is experiencing no force due to capital Q. So electric field, then it determines the region of influence of a charge. Now, if the charge small q is unit positive charge, if it is unit positive charge, if the charge is, if it is unit positive charge, then the force experienced by small q is called the electric field intensity at this point. Electric field intensity at this point, that means at the point where the charge is placed, where the charge is located. So we can define the electric field intensity like this. We can define the electric field intensity like this. Electric field intensity is the force experienced by a unit positive charge. Unit positive charge. Again, we have we know from the Coulomb's law that the force between two charges depends upon the distance between them. Therefore, at different points in the field, the distance of the unit positive charge from the central charge changes. Therefore, the force experienced by it will also change. It means that the electric field intensity is different at different locations in the field. So generally, the electric field intensity is different at different locations. In the field. But this is not always true. In certain situations, it may happen that the electric field intensity is same at every point of the field. Then that field is called uniform electric field. Otherwise, the electric field is called non-uniform electric field. So non-uniform electric field means the electric field is different at different locations, different points of the field. And uniform electric field means the electric field intensity is constant everywhere in the field. But you see, the electric field intensity is a vector quantity. It is a vector quantity, so it must have direction in addition to magnitude. Therefore, when we talk about the electric field, we have to talk about the direction also. So, in uniform electric field, the electric field intensity is same everywhere, not only in magnitude, but also in directions. That means in uniform electric field, at two different points, the electric field intensity will have same magnitude as well as same directions. But in non-uniform electric field, the electric field intensity may be different in magnitudes at different locations, or maybe magnitudes are same but directions different. Or generally, both directions and magnitudes become different. So this is the basic concept of electric field intensity. And normally we do not say electric field intensity. In place of electric field intensity, we say electric field. Electric field at this point is this. It means that the electric field intensity at this point is this. Okay. So now, how to calculate the electric field? It is very simple. You see, again, I am going back to this picture. You see, this is the electric field due to the charge capital Q. Within this electric field, a charge small q is placed. We assume the small q to be unit positive charge, but it is not necessarily to be that. Suppose small q is not a unit positive charge. Then how to calculate the electric field intensity at the position of small q? So we have to calculate the force on small q. What is the force experiencing by the charge small q at this location? We have to find out that. And that force must be divided by the magnitude of the charge to get the force experienced by unit positive charge. And it gives you the electric field at this point. So the mathematical expression of electric field will be this one. mathematical expression of electric field will be E equal to F divided by Q, where F is the electrostatic force acting on Q. It is the electrostatic force acting on the charge small q, and small q is the magnitude of the charge. So whatever be the magnitude of the charge, if we divide the force experienced by the charge by the magnitude of the charge, we get the electric field intensity at that point. So this is the expression of electric field intensity, and from this expression we can find out the SI unit of electric field intensity. It is obvious that the SI unit of electric field intensity is Newton per Coulomb. And we can also find out the dimensional formula, because the dimensional formula of force is MLT minus 2. Okay. The dimensional formula of Q can be written like this, or Q can also be written like AT, A for current. So it is Q inverse. MLT minus 2 Q inverse, it will be the dimensional formula of electric field intensity. So now onward, in place of electric field intensity, I shall use the term electric field. After getting the concept of electric field intensity, now we want to highlight a very important principle, which is called principle of superposition. Principle of superposition. So what is this? Let us see. In the previous page, we have shown the presence of two charges. One charge is at the receiving end. It is experiencing some force, and the other charge may be called as source. But if we have a number of charges nearby, then how to calculate the electric field intensity or electric field at some point? So let me elaborate that. Suppose this is a positive charge. It is, say, Q1. This is another positive charge present here. It is Q2. This is a positive charge. It is, say, Q3. This is one charge. It is, say, Q4. And here this is another charge. It is, say, Q5. Now our question is, what is the electric field intensity at this point? You see, the electric field intensity is different due to different charges, because this point is located at different distances from these 5 charges, and also direction of forces are different. For example, due to Q1, the electric field intensity is this one. Due to Q1, the electric field intensity is this one. It is directing like this. It is, say, E1. E1, since it is vector quantity, so it is, we write it as E1 vector. due to Q2, the electric field vector will be this one. Say it is E2 vector. E2 vector. Due to Q3, the electric field will be like this. It is E3 vector. Due to Q4, the electric field will be like this. Suppose it is E4 vector. And due to Q5, the electric field will be this one. Say it is E5 vector. E5 vector. Now, due to the 5 different charges, we have 5 different electric fields at the same point. At the same point, let us denote this point as P. Then what is actually the electric field at P? So the principle of superposition says that the resultant electric field at P is the vector sum of all these individual electric fields. That means the electric field, resultant electric field at P, EP, let me write it as EP, it is equal to E1 vector plus E2 vector plus E3 vector plus E4 vector plus E5 vector. So whatever be the number of charges, the resultant electric field at a point is the vector sum of individual charges. So it is called the principle of superposition. But mind it, this sum has to be vector sum, not the scalar addition. So we can write the principle of superposition in this way. We can write the principle of superposition in this way. The resultant electric field at a point, the resultant electric field at a point due to the presence of a number of charges is equal to the vector sum of the vector sum of the fields. Vector sum of the fields at that point due to individual charges. So this is called the principle of superposition. So with the help of this principle, we can find out the electric field at a point due to a system of charges. Okay, so next, we should discuss another important concept, which is called electric field lines. Electric field lines. Electric field lines means it is the trajectory of a positive charge in electric field, or trajectory of a unit positive charge in electric field. So what is electric field lines? So these are the electric field lines are the trajectory of a unit positive charge in an electric field. So how to find out the electric field lines? Let me see. We have just to find out the trajectories of unit positive charge. Say this is a positive charge. So it will repel the unit positive charges. If a unit positive charge comes near to it, then it will repel that unit positive charge. As a result, that charge will move away along a straight line. Therefore, the trajectory of the unit positive charge will be like this. Sorry, these are the straight line. Trajectory will be like this. But if the charge is a negative charge, then it will attract the unit positive charge, so the trajectories will be just reverse. This will be just opposite. But if two charges are present nearby, then the trajectory will be curved. Suppose here in this case, we are assuming that only the positive charge is present. There is no charge in the nearby part. And in this case also, we are considering that only the negative charge is present. But if one positive charge is present here and one negative charge is present here, they are near, then the trajectory of the unit positive charge will be like this. This will be like this. Similarly, if two positive charges are present near to each other, the trajectory will be like this, because the positive charge will repel. Okay. So in this way, we can draw the field lines. Actually, these field lines form the map of an electric field. So the density of the field lines at a point, suppose this is a point, this is a point, and we are considering a small area around this point. Now, density of the field lines around this point, it is proportional to the magnitude of the electric field or the electric field intensity at this point. Similarly, to find out the direction of the electric field at some particular point, we have to draw a tangent here. Suppose we want to find out the direction of the electric field at this point, then we have to draw a tangent. So the direction of this tangent will give the direction of the straight line, direction of the electric field. Okay, so this is just introduction of electric field. We have to discuss the electric field lines in details, and it will be done in the next class.